Hello Stat 200 and welcome to the video lecture for Lesson 10. This week we'll be learning about analysis of variance, often abbreviated as ANOVA. In previous lessons, you learned how to compare the means of two independent groups using a t-test. And ANOVA is used to compare the means of more than two independent groups. In this course, we'll just be covering one-way ANOVAs. We call them one-way because they have just one explanatory variable. There are higher order ANOVAs that you'll see if you take an intermediate statistics course. These are the 5 learning objectives that we'll cover this week. Almost all of the calculations this week will be done in Minitab Express. There may be a few questions in the Wiley Plus assignment or quiz where you need to be familiar with the relations between some values and you'll need to add or subtract or divide, but the larger calculations with multiple steps will all be done in Minitab Express. We'll start now with the first learning objective. Explain why it is not appropriate to conduct multiple independent t-tests to compare the means of more than two independent groups. ANOVAs are used to compare the means of 3 or more independent groups. One of the first questions that students usually ask when I introduce ANOVAs is, why can't we just do a series of independent means t-tests to compare all of the possible pairs of groups? In Lesson 6, we learned about the problem of multiple testing. When multiple tests are conducted, the probability of a type 1 error increases. In other words, there's a greater chance of finding statistically significant results due to random sampling variation. The more tests we conduct, the higher the likelihood of making one of those type 1 errors. For example, if we had 3 groups, we would need to do 3 separate independent means t-tests to make all of the possible pairwise comparisons. The actual overall alpha level is not exactly additive, but here the actual overall alpha level would be close to 0.15. We're not going to do the calculation of this in this course, but running 3 independent t-tests, each with a 0.05 alpha level, if there were no significant differences in the population, the probability of obtaining at least one significant result is 0.143. That is a high probability of committing a type 1 error. If we had 4 groups, we would need to do 6 independent means t-tests. The more groups we have, the more comparisons we need to do, and the greater the chance of making a type 1 error. Again, the overall alpha level will be well over 0.05. With 6 independent tests, the probability of obtaining at least one significant result, given that the null hypotheses are all true, is really 0.265. In other words, if the population means for these 4 groups were really all the same, there would still be a 26.5% chance of observing at least one statistically significant result due to a type 1 error. This is a major problem. There are a few different ways to overcome it. In Lesson 6, you saw the Bonferroni correction, where the alpha level was divided by the number of tests. This is one acceptable solution. The most common solution, though, is to conduct a one-way ANOVA. A one-way ANOVA will look at all of the groups together to determine if there is a difference overall. It will hold the overall alpha level to 0.05, so we don't need to worry about alpha being larger due to running multiple simultaneous tests. If the overall ANOVA is statistically significant, then we can make all of the pairwise comparisons to see which groups are different from one another. Before moving on to the next learning objective, I want to summarize why it is not appropriate to conduct multiple independent tests. When we conduct multiple tests simultaneously, the probability of finding a significant result when there are really no differences in the population is increased. In other words, the actual overall alpha level ends up being higher than 0.05. The second learning objective is to use Minitab to construct a probability plot for an F distribution. When we compared 2 means, we used a T distribution. For 2 proportions, we used a Z distribution. Now, when conducting an ANOVA, we're going to use an F distribution. Like the T distribution, the F distribution varies depending on degrees of freedom. The degrees of freedom are separated into degrees of freedom between groups and degrees of freedom error or degrees of freedom within groups. Degrees of freedom between groups is equal to k minus 1, where k is the number of groups. Minitab Express will call this the numerator degrees of freedom. Degrees of freedom within groups is equal to n minus k, where n is the total sample size and k is the number of groups. Minitab Express will call this the denominator degrees of freedom. Degrees of freedom error is also used. In order to construct an F distribution, you need both of these degrees of freedom. When we conduct an ANOVA, the p-value will be the area to the right of the test statistic on this F distribution. ANOVAs are always right-tailed tests. We'll walk through one example now. We have 90 participants divided into 3 groups. Our test statistic is F equals 3.55. First, we need to compute our degrees of freedom for this F distribution. Degrees of freedom between groups, which Minitab Express will call the numerator degrees of freedom, is k minus 1, where k is the number of groups. We have 3 groups. 3 minus 1 gives us 2 between groups degrees of freedom. Degrees of freedom within groups, which Minitab Express will call the denominator degrees of freedom, is n minus k, where n is the total sample size and k is still the number of groups. With a total sample size of 90 and 3 groups, there are 87 within groups degrees of freedom. I'll take you to Minitab Express now to construct an F distribution with 2 and 87 degrees of freedom to find the p-value for an ANOVA with a test statistic of F equals 3.55. The procedure for constructing an F distribution to find a p-value is similar to what we've done in the past with the z and t distributions. I'm going to construct a probability distribution plot to display the probability. When I select F distribution, Minitab Express now asks for the numerator and denominator degrees of freedom. Numerator degrees of freedom is the number of groups minus 1. We had 3 groups and 2 numerator degrees of freedom. Denominator degrees of freedom is equal to the total sample size minus the number of groups. We had 90 participants minus 3 groups for 87 denominator degrees of freedom. We were given an F test statistic of 3.55. Minitab Express considers this a specified X value. F tests are always right-tailed. The p-value will be the area to the right of 3.55. Our p-value is 0.0329563. Most of the time, we'll be running ANOVAs using Minitab Express. When you run an ANOVA using statistical software, it will give you the p-value, just like it did with the z and t tests. There may be some questions on the Wiley Plus homework assignment this week, though, that make you look up a p-value by making an F distribution, and that's when you'll use this procedure. We'll go back to the PowerPoint slides now to cover our third learning objective. Our third learning objective is to use Minitab to perform a one-way ANOVA with Tukey's pairwise comparisons. Before we go back to Minitab Express, I want to run through the 5-step hypothesis testing procedure for an ANOVA, and I want to introduce you to Tukey's pairwise comparisons so that you can see what the software is going to be computing for you. We'll start with a one-way ANOVA. Step 1 is to write hypotheses and check assumptions. With a one-way ANOVA, we're comparing the means of 3 or more groups. The null hypothesis is that the means are all equal. I write this as mu for group 1 equals mu for group 2 all the way through mu for group k. Recall k is the number of groups. The alternative hypothesis is that at least one pair of population means is not equal. I write this as at least one mu sub I does not equal mu sub j. where I and J are just labels for two different groups. There are three assumptions that we should always confirm are met before using the F distribution to approximate the sampling distribution. 1, the samples are independent. In other words, there are different cases in each group that are in no way matched or paired. 2, the response variable is approximately normally distributed, or all sample sizes are at least 30. If this assumption is not met, randomization methods may be used. This is the same randomization procedure that we learned back in Lesson 5. We won't cover this in this course, but it can be done in StatKey. And our third assumption, the population variances are equal across responses for the group levels. To check this assumption, we compare the largest sample standard deviation to the smallest sample standard deviation. The largest sample standard deviation divided by the smallest sample standard deviation should be less than or equal to 2. In other words, the largest standard deviation should not be more than twice of the smallest. If this assumption is not met, a randomization test may be used, or there are other methods that don't assume equal variances. We won't be covering these methods in this course, but just be aware that there are other procedures available when assumptions are not met. Those alternatives tend to have lower statistical power, so when assumptions are met, a one-way ANOVA is preferred. Step 2 of the 5-step hypothesis testing procedure is to compute the test statistic. For a one-way ANOVA, we'll be computing an F test statistic. This is because the sampling distribution is being approximated by the F distribution that we saw in the last learning objective. The hand calculations for an F test statistic are not difficult, but they require many steps. In this class, you'll be working primarily with Minitab Express, which will do all of those calculations for you. Conceptually, the F test statistic is a ratio, or a fraction, of the between groups variability to the within groups variability. MS stands for mean squared. This is a measure of variability, which we'll see in a second. This is known as the ANOVA source table. Minitab Express or any statistical software will give you this table when you run a one-way ANOVA. It's essentially showing you all of the calculations up to and including the F test statistic. The table separates variance as between or within groups. SS stands for sum of squares. This is the same sum of squares that we saw back in Lesson 2 when we computed the variance and standard deviation for one group. SS between groups is a measure of how different the group's means are from one another. SS within groups is a measure of how different individuals within each group are from one another. SS total is equal to the sums of squares between groups plus the sums of squares within groups. If we were computing the variance or standard deviation of the response variable, ignoring the different groups, the sums of squares total is what we would divide by n-1 to find the variance, and then take the square root of to find the standard deviation. The degrees of freedom here match the degrees of freedom that we computed earlier when we practiced making an F distribution. MS stands for mean squared. This is a measure of the variance attributable to the differences between groups and differences within groups. If we divide the variance between groups by the variance within groups, we get our F test statistic. Because it's a fraction, this is sometimes also called the F ratio. The last column in the ANOVA source table is the p-value. Like I said, if you're using Minitab Express or statistical software, it will make that F distribution for you with k-1 and n-k degrees of freedom to find the area to the right of your test statistic, which is the p-value. This is actually the third step of the 5-step hypothesis testing procedure. Step 4 then is to make a decision. We have the same rules as before, assuming a 0.05 alpha level. If the p-value is less than or equal to 0.05, reject the null hypothesis. P greater than 0.05, fail to reject the null hypothesis. Step 5 is to state a real-world conclusion. If you rejected the null, then there is evidence of some difference in the population means. And ANOVA will not tell you where those differences are. If we want to know where the differences are, we'll need to conduct a post-hoc test, such as Tukey's pairwise comparisons, which we'll see soon. If you failed to reject the null in step 4, then there is no evidence of any difference in the population means. If you fail to reject the null, then you typically don't do any post-hoc tests unless there was some original research question concerning pairwise differences. We'll move on to the topic of Tukey's pairwise comparisons now. The one-way ANOVA will tell you whether or not there is some difference between some population means. The initial results will not tell you which groups are different from one another. In order to determine which groups are different from one another, a post-hoc test is needed. Post-hoc means after, so these are comparisons that are conducted after the one-way ANOVA. There are many different post-hoc analyses that could be performed following a one-way analysis of variance. Here we'll just learn about one of the most common tests, known as Tukey's honestly significant differences test, also known as Tukey's pairwise comparisons. Most statistical software, including Minitab Express, will compute Tukey's pairwise comparisons for you. This specific post-hoc test makes all possible pairwise comparisons. This analysis takes into account the multiple tests that are being performed and makes the necessary adjustments to ensure that the type 1 error rate is not inflated. For each pair of population means, Tukey's HSD is testing these hypotheses. The null is that the population means are equal, and the alternative is that the population means are not equal. We'll go to Minitab Express now so I can show you how to conduct a one-way ANOVA there with Tukey's pairwise comparisons. This will lead nicely into the last two learning objectives, which involve interpreting these results. This is the Spring 17 data MTW file. These data were collected from a representative sample of World Campus Stat 200 students. The variable labeled preferred beverage had 3 different options. Participants could choose between beer, water, or wine. We're going to compare the weights of participants who chose between beer, water, and wine. Since we're comparing the means of 3 independent groups, a one-way ANOVA is the appropriate analysis. When we run this, Minitab Express will give us the descriptive statistics that we need to check the other assumptions related to sample size and standard deviation. I'm on a PC, but the steps are the same for a Mac. Go to Statistics, ANOVA, One-Way ANOVA. The default is that the responses are in one column for all factor levels. What this means is that we have one column for the response variable and another column for the factor. There's an example in the online notes where the responses are in separate columns for each factor level. The response variable is the quantitative variable that is being compared between the groups. Here I said that we'd be comparing weights. Factor is the explanatory variable. This is the categorical grouping variable. I said that I was going to compare participants based on their preferred beverage. Under comparisons, Minitab Express offers 4 different post-hoc analyses. The only one that we're covering in this course is Tukey. Under the Graphs tab, there are different options for graphs. I usually leave this as the default. Now, Minitab Express will give you a lot of output. The table labeled Analysis of Variance is our ANOVA source table. When we conduct our hypothesis test, this is where we'll get the F test statistic and the p-value. The means table gives us the descriptive statistics. We'll use this to check that each group's sample size is at least 30 and that the standard deviations are similar. If we scroll down, we have two different tables for Tukey's pairwise comparisons. I'm going to take you back to the PowerPoint slides now, and we'll interpret all of this output there because it's essentially our 4th and 5th learning objectives this week. Learning objective 4 is to interpret the results of a one-way ANOVA. We're going to use the 5-step hypothesis testing procedure to do this. Step 1 is to write hypotheses and check assumptions. The null hypothesis is that all population means are equal. I'll write this as mu for beer equals mu for water and mu for wine. The alternative hypothesis is that at least one pair of population means is not equal. I write this as at least one mu sub I does not equal mu sub j, where I and j are interchangeable labels for any of these three groups. We have three assumptions. First, samples are independent. This assumption is met because we have different people in each group and they are in no way matched or paired. Second, the response variable is approximately normally distributed or all sample sizes are at least 30. I'll pull up the means table here. Our sample sizes are 86, 308, and 105. All sample sizes are at least 30, so this assumption has been met. Third, population variances are equal across responses for the group levels. We'll compare the largest to the smallest sample standard deviation. The largest was 47.711 and the smallest 41.053. 47.711 divided by 41.053 gives us a ratio of 1.162. This is less than 2, so this assumption has been met. Step 2 is to determine the test statistic. For this, I'll pull up the ANOVA source table from Minitab Express. The test statistic here is the F value. F equals 4.88. Step 3 is to determine the p-value. We can get this value from the ANOVA source table as well. P equals 0.0080. If this were reported in an article, it might be written as F with 2 and 496 degrees of freedom equals 4.88, comma, P equals 0.0080. Step 4 is to make a decision. Our p-value is less than the standard alpha level of 0.05, so we reject the null hypothesis. And step 5, state a real-world conclusion. There is evidence of some difference between the population means. This doesn't tell us where the differences are, though. To determine which groups are different from one another, we need to conduct a post hoc test. The post hoc test that we're going to use in this course is Tukey's pairwise comparisons. This brings us to our last learning objective. Interpret the results of Tukey's pairwise comparisons. These are the two tables that Minitab Express provides for us. We'll look at each of these now. The first table provides us with grouping information. Means that do not share a letter are significantly different. Beer is only in group A. Water and wine are both only in group B. This means that beer and water are significantly different from one another. Beer and wine are significantly different from one another. Water and wine are both in group B, so they are not significantly different from one another. The second table provides us with 95% confidence intervals and test statistics with p-values for each possible pair. Note at the bottom, individual confidence level is 98.03%. Minitab Express took into account the number of comparisons that it was making, and it adjusted the confidence level and it adjusted the p-values for us. We can now interpret these values without needing to worry about multiple testing, because those adjustments have already been made for us. My preference is to look at the adjusted p-values here. If the adjusted p-value is less than or equal to the standard alpha level of 0.05, then we reject the null and there is a statistically significant difference. If the p-value is greater than 0.05, then the difference is not statistically significant. Here, the water and beer pair and the wine and beer pair both have p-values less than 0.05. So these two pairwise comparisons are statistically significant. The wine and water pair is not statistically significant because the p-value is greater than 0.05. We have covered all 5 learning objectives now. If you're looking for more examples, there are some in the online notes. As always, if you have any questions, please post them to the Lesson 10 discussion board on Canvas.